In the lab, in addition to this, discussion for movie recommendation engine, in the lab you will be doing a similar one for jokes. Okay.
Okay.
So both are coming in this exam, in this article. This is the quintessential software in R recommender lab that actually it was developed by Michael Hashfler. And so we will really be benefiting by his contributions to the science. And it was published in, I think it was published in Journal of Applied Statistics, something like that. Okay? We won't talk about all these sophisticated symbols and so on. Okay, all these kinds of things. But you know what I'm
It
talking
looks dry to read.
Yes. Yeah, looks like that. Yes. I never heard of that kind of comparison before. It's very funny. My purpose is really to make sure that you understand the full scope of recommendation engine, because AI is about recommendation, really, if you think about it. These are all some foundations. Your chatbot is about recommendation, or in general, if you are going to work with AI, it's going to show you for a large class of problems, this is the kind of solution. Let me put it this way, okay? Not everything has to go through this kind of solution, but for a large collection of problems in marketing, in business, in ordinary day-to-day life, it is about recommending something, because that's what we are asking AI to do, right? We want AI to recommend something for us, and it's going to become ordinary walk of life in our life. We will just look at the watch and ask for something, and that's an AI that will recommend something, right? So that's why I want to spend fairly some good amount of time. So we'll come to that. Okay. So let's review one more time the movie recommendation engine. Okay. You are able to see my R screen, right? Okay.
Yes, sir.
Yes.
So I am reading. You understood already. It is about finding similarity. Between if you want to recommend on the basis of the user experience, then you want to see who are all the people who are closer together. So in terms of their interests, the interests are reflected in the scoring, right? It is the interests are reflected in the when I say something I like most or not I do not like, I am expressing the preference, and that is interest and preference. And if I more often resemble, my interest more often resemble like Anto's, then it makes sense that whatever I did not use it, whatever Anto used it, it could be a potential recommendation for me, because I resemble like him in most of the likings and in most of the non-likings. Okay, that is the simple principle by which the recommendation engine works. So I was also, let me go back to this presentation deck. So opening. Okay. So I discussed in detail that stuff. So what we are saying, so it could be user-based or it could be item-based also. Okay. So in other words, similarity among users is one way of recommending. And the other one is similarities on the basis of items. Okay. Same thing. If collection of items, 8 items in this case. I didn't go through that part, right? I was going through only these similarities on the basis of the users only. I could have created the cosine similarity between the item 1 and item 2, item 1 and item 3, item 1 and item 4, item 1 and item 6, like that. I could have created that also, isn't it? So when I do that kind of comparison, again, I can say, well, this user hasn't used item 1. Let's say this item 1 is more similar to item 5. Okay, it looks like that to me. Okay? Somewhat more similar, because there are a lot of questions otherwise on the column side, right? More similar to item 1, maybe item 8. Okay, more similar to item 1 is more similar to item 8. Okay, or item 5. Next one is item 5. Let's take item 8. So because they are similar, so I can recommend potentially for the user the item, we are talking about the item 8 is here and item 1 is here, right? So, and I'm saying they are similar, not in this way. Row-wise similarity is not what we talked. So we talked about row-wise similarity here, remember that, okay? This row-wise similarity, which is user-based. But I'm saying I can also do similar things item-based. And I'm saying if I1 and I8 are more similar and looks like more similar, because whatever I have there, they're pretty good, okay? So these 3 things are pretty good here, okay? Whatever we don't have, we don't have to worry about it. So what we are saying is now, so item, I can fill up, that's the point. I can fill up number 3 here for this, okay? And I cannot fill up here, okay, because both sides I don't have much information, but I can fill up for item, for the user 2, he is more likely to be user 2 is more likely to be also using item 8, okay, because he like item 1 so much. 3 and above is better. 3, below 3, 1 and 2 is not good, right? Because low value. So the idea is that we can recommend on the basis of the users or on the basis of the items. Okay, so take that message. Now let me go back to the R. So we are going to do such comparisons later on. So now I'm reading the movie data. I am also reading the ratings data. Okay, and there are 9,125 movies on 3 variables, and here is the first. Let's take a look at that. We take a view the movie data basically, right? And I think it is already there. I have already executed the command, and it is here. This is the movie data. So here it may not be big. Let's see. Okay. Are you able to read this one? So first movie is, this is the movie IDs. First movie is Toy Story, and it has we can characterize the movie, tag the movie as maximum of 10 different genres. Okay, and here it is adventure. It is also tagged as animation, children, comedy, and fantasy. Right, and the second movie is Jumanji. It is adventure, children, fantasy. Third movie is Grumpier Old Men, and it is comedy and romance. Okay, Walking to Exhale is comedy drama performance. Father of the Bride Part 2 is comedy. Okay, so that is what we have as the movie data. Now, in terms of the ratings, so we read the ratings, and let's see the ratings data. Here is the rating data. After I read that rating data, I have here. There are n number of users. We'll figure out, find out how many number of users are there, and that user has seen movie ID 31. So movie ID 31 is, I also opened that. Let's see, Excel sheet. Yeah, I also opened the Excel sheet here for ease of reference. And movie 31, we can see here. Okay, so control home. Movie 31 is Dangerous Minds. It's a drama. Okay, and then what else the user one is watched, and and given a rating, and these are all good ratings, right? The anything above 3 is considered good. 3, 4, 5 is considered great, and anything less than that is considered as not so great. So we will use such a binary classification, okay, to just quickly understand. So what is the next movie I want to see? Yes, in 10 at 10:29. So he has seen Dumbo, animation, children, drama, and musical. Okay, let's just see what are the other movies he has seen. Okay, because I will recall these things when I finish the validation. Okay, and then what are the other movie? 1061. Okay, so let's go because I lost this condition. Search 1061. So it's a thriller. Okay, so far drama is the most common thing, right? But it's okay. These are all, some correlation is there because you can't go by only one word. We want to see how they look similar, right? People with the similar movies rated high. So he has rated 1061 as 3 good. Okay, 3, that's sleepers. Okay. So let's say one more movie, 1129, right? But I don't go there. I have to go here, 1129. So here it is. That is Escape from New York. It's action, adventure, sci-fi, and thriller. Okay? So these are the movies he saw, and then he rated them like this. Okay. Now let's go to the. Um, so remember that it is very hard to translate your knowledge about what you understood about similarity, taking the average of people, all those things, and implementing it yourself in R is very difficult. So we are going to use a package called Recommender Lab that was created by Michael Hostler. Okay, and so sometimes you have to transform the data in such a way that the Recommender Lab will accept that data, okay, as an input. Okay, so there are some transformations we have to do. So before that, we are going to explore the data. That's what we are trying to do here. Okay. So the movie genres, so movie genres are we know that it's a blob of information but separated by pipe. So we just take a look at that one, separate the pipes here, and then see how we can view that easily into a tabulation like this. So here is that's what it is. So there are 18 remember 18 genres are a total of 18 genres: action, adventure, animation, children, comedy, crime, documentary, drama, fantasy, film noir, horror, musical, mystery, romance, sci-fi, thriller, war, and western. These are the 19 things. Okay, and we want to separate out those ratings data, right? Not ratings, the movie data, right? Separate out the genres. Okay, so so that's what we are trying to do here. Some processing here for all the movies, but before we do that, we create a matrix of zeros, and then put one wherever this particular keyword you find it in the genre. Okay, so that's what we are doing here. So don't think anything else is happening here. Okay, so after I do that, I was checking what is the dimension of the movie genre. So it should be only this dimension, isn't it? Okay, let's see. So I ran that. If I ran that, it says 9,125, and then and then we have 18 genre types, right? So first we define that and structure of the genre matrix too. Okay, so basically, I find that now this is 9,125 movies, and these are the genre types. And the first one is what is this? 1, 2, 3, 4, 5, 6. What is the sixth one here? Sixth one is 1, 2, 3, 4, 5, 6. Crime. Okay. Crime. And then the next one is not documentary, not drama, but fantasy. Okay, that's what this means, fantasy, and then film noir. So that's how we translate that into 0 1s, because see, whatever you have in, characters or the qualifiers, you still have to convert them into numbers so that you can do the calculations, computations, and so on. Your computations are always in numbers, even in the, oh boy, 1 second. I have to put, okay, sorry. So even in the, don't worry about it, it should come back. Sorry. So even in the NLP, we convert them into numbers. Remember that, okay? That's how we can do the computation. In a product, distances, similarities, averages, all those things, we can calculate only if we convert them to numbers. So in this case, the question of whether that particular genre is there in the particular movie or not. Okay, that's all we are converting. And then all these codes. Okay, I will give you this code. You have to figure it out why it makes sense. So why it makes sense. You have to figure it out because otherwise, you will feel that's kind of it is not sticking, right? So, for example, to make I made a huge matrix of zeros, 9,126 rows, but because the first one is a header information, for 9,125 by 18, I put wherever wherever I have the particular genre is there. Okay, that's what this code is about. So for index in 1 to end row of the movie genre 2, and what is movie genre 2? Movie genre 2 is the list of movies that is coming from, okay, genre 2. Where is it? I already defined this. Okay, so here it is. So movie genre 2 is basically the whatever the split that we did. Okay, so if you look at that information, you can always check. Whenever you have doubt, you can go back and view what the data is. But not everything you can look at it. Remember, if it is matrix, you can look at it. If it is data frame, you can look at it. If it is a list, it's complicated. You know that, right? List is complicated. You got to put double square bracket, triple square bracket, and so on. If it is a list of a list of a list, then you have to put triple square bracket. Am I making sense to everybody? So if it is a list, you have a more complex way of searching and looking at the data. But if it is straightforward, this one is a straightforward data frame. So you can say we can look at genre 2, okay, movie genre 2. It's just a transformation, okay. Don't worry about it, but we are just trying to explore the data because exploring the data first is very, very important. Okay, so this is what it is. The first movie is adventure animation. It's basically split the data, right? And wherever adventure here we have for each of these movies, we will place them into one or not. That's what it is. Okay. All right. So let me go back to the codes. I'm trying to explain the codes. The code session is going to be only about the codes today. And even though there are 18 or maximum 18 is there, every movie is only categories up to 10, because if you put all the 18, then it's not really a discriminating information, right? Every movie, if you give a movie for all these things, it doesn't make sense. That means we don't know what we are doing, right? That if somebody says, oh, I like everything, and now it's not just a question of liking, it's about tagging that, right? This movie is action, adventure, animation, children, comedy. It doesn't make sense, right? If it is children, how could it be horror, right? So how could it be thriller and so on? So we give only 10 possible tags. So that is remember, if you want to be a great data scientist, I already told you a few things. Okay, one is you have to know the story of the data. This is what we're talking about. Okay, just because somebody gives the data, don't assume that you understood the data. Very, very important. Okay, so this is about not only understanding the data. The second part to that is parse out the data, understand what is going on in the data. So they will tell you the story about the data, for which you will have to do the analysis. That's one part of it. The second part is, after having heard of all those things, you want to look at the data. You make sense. This data means something, right? Rows are movies, columns are genre first, and then users, the rows are users and the columns are ratings. Okay, but the interesting thing is that an user can come multiple rows when he gives the ratings. Now we saw that, right? The rating data, and user can come in multiple times. This is user one, so many times come here. So it is what is called the long form. Okay, so now you have to think about long form data to row by column type data, because you have to bring it row by column data in order to do your distance calculations, similarity measures, comparisons, correlations, all kinds of things. Okay, so you cannot keep the long form data as it is to do your analysis. You have to transform it, and that's where the decast comes. Now I showed you reshaping. Reshaping comes there. Okay, so you have to parse the data, makes sense out of it. Then eventually it comes down to basically doing, I'll tell you another point, right? What do you do really in data science calculations? You eventually, basically do weighted calculations of the data points, right? Regression is a weighted calculation. Do you agree with me, everybody? It's a weighted calculation. You are giving weight y is equal to alpha plus beta 1, x1 plus beta 2, x2, right? You are giving the
Yes.
variable, independent variable x1 weight beta 1 and independent variable x2 weight beta 2. Do you agree with me?
Yes, sir.
Yes.
Please remember
Yes,
these
sir.
things. This is when you come up to that level of thinking, you see everything is really about giving weights. Really, that's what it is. Okay, it's so that when you give the proper weights, your prediction becomes more valuable. Okay, it's not all factors, all attributes, or all variables have equal weights. That is what differentiates the decisions, people, processes, products, right? So if you take a flower, you'll say this is a very reddish color. So you're giving a lot of weight to that fact of red, and it has petals, long petals. You are giving weight to the long petals. You are giving, but that means that if you are talking about the length as an important factor, then you are giving that important factor a high weight. So it is all about decision making is all about weighted calculations. So please note it down if you want. These are the things, it has to free up your thinking. It's not a magic that somebody could think and innovate algorithm. You could do the same thing also. So, I'm coming back one step now. So you have to know the story about the data as well as understand what is going on in the data that you receive, and that's what we are trying to do here, right? But why do I do this kind of parsing? Because this is how I can do the computational work, numerical computation work. Okay, and I converted the each of the movies genre characterization into 0-1 data, whether that characterization is there or not. That's what it is. Okay. Okay. So let me go back to this Java matrix 2. Okay. All right. So let's keep continuing processing our understanding. So far. And then, because I want to convert this data into sparse data, I will have to make wherever there is no, in fact, this is about what, okay, let's go back to this one. So whenever there is no data, we want to make it a NA. That's a sparse definition. See, in fact, almost 80% of the data will not be there. Am I making sense to you? For example, in the user rating, 80% of them will not be there. Okay, there is 100,004 user ratings are there, but nonetheless, most of the movies will not be evaluated by most of the people. So, and these are all huge data science problems. Remember, even the small movie calculations like 9,000. How many movies I have? 9,020, 9,020, 125 movies, right? So even with this, the data is huge because 9,120, and then I have, for each of the movies, certain number of, not certain number, each of the movies are evaluated by n number of users. So user rating and movie list, everything becomes huge data, right? So the recommended lab utilizes the principles of sparse matrix storage and calculations. Okay, so that's what these NAs are all about, and the NAs are temporarily converted into zeros. Okay, so we can also it is hard to search this one genre matrix 2. Let's see what is genre matrix 2. Oh, we are no, not this one. View. Sorry. View genre matrix 2. Whether I have it here? Yeah, here I have it. This is your genre matrix. Okay. Adventure, animation, children, comedy. That's the first one, right? Class 2. Fantasy. Okay. Do you see this one? What I'm saying? So it is coded. All right. Now, but then, as it is, we don't know what it is. So we just want to check one more time. That's where, we are doing here some calculations. So we combine movie data, first column and second column, with the genre matrix, and then looking at the genre matrix. That's what it is all about. Okay? So if you do that, let me see whether I did that already. So the first movie is Toy Story, and after I combine these first two columns from the movie data to this genre parsing, it is connected. So I know exactly. So for example, I can go, what is this movie? That is the fifth movie, right? So fifth movie refers to, I go back here. Fifth movie is Father of the Bride. Okay, I don't know how many of you saw that movie. Let's go and see what are the genre types noted here. Father of the Bride, it's a comedy. Yes, I know that much. Okay, because I have seen that placement. What else is there? Well, so far that's the only thing. Fifth one, right? Comedy. That's it. It's just a comedy. Okay, not many attributes are given. Okay, so go back. This is just coming from the data. I just parsed the data in that way. So let's take the last one. Heat. It's about action. I think I have seen it. I think I have seen this movie long time back when I was in graduate school. Is it possible? Yeah, that is correct. When I was graduate school, no. I was not graduate school at that time. I was working actually. So not in
Think
graduate school. Maybe it came
Al
late.
Pacino. Al Pacino.
Al Pacino. Where is that? Yeah, you mean the movie?
Yeah.
Do we have it in the list?
No, I mean the Heat. I think.
Oh, it is just a movie. Let's say it's an action movie. It says, and then let's see characters. Okay, so it is also crime. Yeah, something like that. I remember very vaguely. Okay.
Yeah, I think so.
Yeah. So two of them are for there. Oh, it's a thriller too. Yeah, something like that. I remember very vaguely. But I thought maybe it is summer heat, not heat. I don't remember. Okay, I was seeing it. You won't believe. I saw it in Dallas, here in Dallas, when I was when I was a graduate student for economics at SMU. I mean, I never see movies and so on. It so happened. Open a theater, the kids were calling, let's go out and see the movie. I was saying, what is the movie? I didn't even know what it is. And then I was just sitting and watching there. But I remember something, maybe it's summer heat, I don't know, or heat, because it was way back before 1990. Okay. So this is, it is just, I'm just exploring and then making sure that I understand the data. Very, very important. Are you having difficulty in hearing me out by any chance, everybody?
I'm sorry.
No,
Any
sir.
of you having difficulty in hearing me?
No, we can hear you.
Yes,
I
sir.
can hear you.
No problem, because it keeps coming back, again and again, audio restored, and so on. Okay. I think I don't know what one day this computer is going to fail. It has been creating some problem of it. All right. So then I have to convert the data into what is called according to recommended lab, I have to convert into what is called the real rating matrix class. It's a particular class of data type that is created specially by Michael Osler, for doing the calculation. So before I do that, for the movie recommender system to make sense of our ratings through recommended labs, we have to convert our matrix into a sparse matrix. And this new matrix is of the class real rating matrix. This is performed as follows. Okay. So we first and foremost, we need to convert that into a, move it to user ID versus movie ID data. Okay. User ID versus movie ID data. And then within that, within this casting, this is called casting, which is row, which is column. Within that one, we are going to, give the rating value. Okay, right. That's what it is. And then we convert it into a matrix. Okay. Not only that, we remove the user ID. See, it is the user ID as movie ID. Rows are user IDs, columns are movie ID. Okay, and then we are converting it into a matrix, as a matrix, and then remove user IDs. Convert rating matrix into a recommended lab sparse matrix. That is the next. That's what the next one is. That is this condition as rating matrix, real rating matrix within quotes will convert it to sparse data, and then we will take a look at this one. Okay. So that's what we have run. We'll run it again for now. Okay, so it is the S4 class, S4 class. There is S3 class and S4 class in R. You should know all these things. For me, the simplest thing is that S3 class is the one which accesses the objects, with the dollar symbol. And S3 class, and then S4 class is the accesses with @ symbol. Okay, there is some advantage with the S4. That's the latest one. But most of the time, we still use a lot of things are used with, with the dollar symbol, okay, to access members, the object members, and so on. So there are actually 671, 671 users are there. That's what this means. By doing this casting, decasting, data casting, that's what is used to using the reshaping, which is the reshaping. So each of the users, somewhere in 9,066, for 9,066 movies, they are given some rating. That's what this means. Am I making sense to you so far? And it reduced from 9,125 because some movies did not have ratings at all. Something happened, we didn't have ratings. I don't know, it could be the latest movie or the old movie. People never got a chance to look at it, even though the recommendation engine recommends, what is called the long tail distribution data. So here is the important terminology. You want to note it down. See, sometimes when I say, you just write down these sentences or keywords. Okay. So recommendation engine it's a long tail opportunity algorithm. What do I mean by that? When you when you got 100,000 movies, first of all, let me ask each one of you, how many movies do you think you have seen in your life? Just give me an estimate. Full movie, you have seen it. You might just surf and then run away. Okay, we are not talking about that. How many full movies do you think you have seen?
200.
200. Let's take that. 200. One. What else? Who else?
100, sir.
100.
100.
Gaushali is 100. Anto is 200. Go ahead. Nini?
Maybe 150.
150. What about Sharanya? How many, Sharanya, do you think? Hello? Okay. I don't know whether she's there or not, but I would say I have seen Sharanya. She's there. Okay. 60 to 70. I think probably I'm also 100 to 100 maximum, right? But you know how many movies are there? In fact, Anto is including Tamil movies. Am I correct, Anto?
Yes, sir.
Yes.
Partly.
But Tamil movies, some of you probably include Telugu movies or Hindi. In addition to English, I'm talking about just, English alone has something like 120,000 movies. Only, so here is, Sharon says, I'm only including Tamil movies. So, what I'm trying to say is, what percentage is 200? Let us say 1,000 movies, right? I don't think we have seen 1,000 movies, right? Nobody sees those. Most of us don't see them. So it is 0.1%. Do you see what I'm saying? There are so many movies we haven't seen, and we don't have time. But the problem is there is so much production is happening, and by recommendation engine, the recommender engine unearths, brings out movies which have never you heard of it. It's a possibility, right? That if you look at the retail store, if you go to Walmart, there's probably just in a store, there are probably thousands of products there. How many of them you use on a daily basis or even in your life? Many of the products, I don't even want to touch them. I don't know what is there and so on, right? But that's a different problem. The point is the recommendation engine, it will say it makes some of the products which are unknown or not people doesn't have a chance to see. When it gets recommended, it gets seen and it gets popularity. Here is one great example. There's something about Himalayan expedition, right? That's a classic example. That movie it's impossible, to get the attention of people because people are so busy with whatever they are doing, right? And few movies get enormous popularity. So that movie about Himalayan expedition, because of the recommendation engine, it got viewed by so many people because it belonged to a class of movies which let's say thriller and action, feature film, thriller, feature film, action. It had a chance because Netflix showed it by the recommendation engine. Otherwise, nobody would have seen it. And I'm telling you, there are 99% of the movie which none of us have seen. And I can tell you, a lot of people haven't seen. A lot of people. So that is called long tail distribution because it's a huge, are you looking at my face? I don't know whether you're looking at my video, right? There's a huge spike. There's short number of movies, right? People see, and then it decreases, and then it goes long tail. This movie is seen only by 10 people or 100 people, like that, okay? It goes on. That is called long tail distribution. So long tail distribution gets attention because of the recommendation. Okay. Now, why did I say that? Because some movies did not get even get the scoring. That's why. Why is that? Okay. Some movies. So we have eventually only the rating matrix is a long data, right? Remember I said that it's a long data. Let me go back and tell you. This is the long format. This long format has been taken. First row is the user ID 1, and all 9,066 movies, wherever he has given the score is filled up. So most of them are NA. You understand what I'm saying? Why I'm saying it is a sparse data? Excellent. Yes. Most of the values are NA. So it needs to be stored in an NA format. I'm sorry, the sparse format. Okay, it's called sparse matrix. So it is automatically converted that. It casts the data in the right way, rows and columns, okay, and it has also stored it in a what is called the sparse matrix form. Okay, so that is done. Is a matrix of real rating matrix with even though there are 100,000 ratings are there, when you post it, most of them will be blanks, and then we want to see the we want to build the recommendation model, period. Okay, so it is recommendation model is recommended registry, get the entries, data type is equal. So I use this data type, okay, real rating, because there are many ways to ingest the data. This is the way. Even within recommender lab, there are many ways to ingest the data, but we are ingesting the data using what is called the real rating matrix approach. Okay, and once you ingest the data, we check from recommender registry all possible entries. Okay, and then what are the names of the recommendation models, and then we are also looking for the description of the recommendation model. So when I run that one, and after that we see all the descriptions of the recommendation model members, and then we are going to only look at item-based collaborative filtering parameters. Okay? That's what we are doing. So far, so good. Build the recommendation model. Very straightforward, isn't it? Just feed the ingest the data real rating matrix. Okay. Let's run that one. And so here it is. Okay. And it comes here also. So these are all different ways we have, performing the recommendation engine. You can see SVD approach, okay, singular value decomposition approach, user-based collaborative filtering, item-based collaborative filtering, just by popularity alone, going with popularity alone, okay, and then random real rating matrix results, random recommendation engine, alternative least squares recommendation engine, and then hybrid approach. These are all some of the common things people use it, okay? And we are going to see a few of them, okay? Not everything, not necessary. So, and it is describing what it is here, that's what it is. So it is hybrid recommender that aggregates several recommendation strategies using weighted averages, okay? The other one, alternate least squares method, is recommended for explicit ratings based on latent factors, okay? Calculated by alternating least squares algorithm. So I haven't taught you alternating least squares algorithm. It's a special class. Maybe I should do a meetup, but sometimes it is useful. But most of the time, remember, even though there are 8 to 10 different methods, how many methods are here? Let us say 10, 11 different methods are there. You remember, life is always like that. 2 of them will be used most often, right? 90% of the, I would say 90% of the time, 2 things will be used, or 3 things, not, okay? So you don't spend your time, it's okay for a researcher, it's fine, but you just use the user-based. Most of the recommendation engines are user-based, okay? And SVD-based, okay? So SVD is the singular value decomposition. See, that's where I'm going, is singular value decomposition. And you will see, and I want to share with you now why I was talking to you in the beginning, that I wanted to get your attention also eventually for the comparisons. And you can see that here is the graph, okay? Here is the graph in terms of the true positive rate versus false positive rate. Do you remember this, Ren? True positive versus false positive. That is your AUC curve.
Confusion matrix.
I'm sorry, confusion matrix. Yes, but also AUC curve. I didn't spend time with you on that. Little bit it got our program. Our batching got a little bit out of sync.
Yes.
You didn't get to hear that, but I will be bringing back into supervised algorithm later. Okay.
Okay.
But you might especially you might have heard of this true positive versus false positive because of your previous experience, right?
Yes.
That is what you AUC curve, the area under the curve, right? This is the area under the curve for recommendation engine. So there is a way to do that. The validation method. These are the comments. These are the commands. Okay. So what are those commands? For example, here is the command. Okay. Algorithm list. We are using only those algorithms, and then we are evaluating for validation, selecting 1 movie at a time, 3 movies at a time, 5 movies at a time, 10 movies at a time, 15, 20 movies at a time. Okay, taking that, we are evaluating. This is just jokes, but we do the same thing for movies also. Okay, so we do the same thing for movies also. Here is for the movie recommendation. So I went there. So this is what gives you, true positive rate versus false positive rate. This plotting, this is what is giving you. For 15% false positive rate, you are able to predict 50% accurately. That's what this says, isn't it? Everybody, including Nini, this gives you, for a given false positive rate, you cannot avoid false positive, right? That means you will wrongly conclude it is correct, true, but
True, yes.
you cannot avoid that. But for a small loss on the false positive, if you can achieve a great true positive, that is good. Look at this one. For 3% error on the false positive, wrongly concluding, you are able to accurately predict 17% of the movies recommended. But if you allow 15% of the false positive rate, you are able to go up to 50% of recommendations. Okay, which is huge in my opinion. Okay? That is 4 out of 1 movie is pretty bad, but then 3 movies are 4. No, this is 4. No, this is 3. Okay, so 4 out of 1 movie is wrong, but then 3 movies are good. That's what this means, isn't it? Right?
Yes. Yes.
So it's a good algorithm. So we know get confusion matrix for the recommendation engine. Also, we can do that. This is 1 movie, 3 movie, 5 movie, 10 movie, 15, 20 movies we take, we calculate them. But as you have more movies, obviously you are going to get more accurate, higher accuracy. Okay, that's what this means. Now, so let me go back. So I'm quickly connecting with you. These ideas. And recommender engine will get you this. Confusion matrix, all those things. So let's go there to my notes again here. So that's what is. This is just explaining it to you, right? In terms of what these recommender algorithms are. Implicit real rating matrix, recommender for implicit data based on latent vectors calculated by alternating implicit data. This is explicit data. Okay, that's a difference, 2 different methods there, even within the ALS. Recommender based on item based, I talked about IBCF is item based collaborative filtering. LibMF or libmf is a matrix factorization with libmf via package RICO system. Okay. There are different factorization. Matrix factorization is using libmf package to do that, but I don't care about it. I just straight away go to. Of course, I look at the randomness, randomly assigned, because we need to compare that always the random assignment. So that's fine, but this is what I recommend that based on SVD approximation, okay, with column mean imputation. Okay, so this is the one I usually would be interested in. Besides the user-based, user-based and SVD is what I look for, and you will see what the results are. So I want to go back there and show you. Let's go back here. The picture, you will know what I'm talking about. Okay, so here it is. Yes, that is correct. This is the one we were talking. As the number of top end recommendation increases, the true positive rate increases, also as positive rate increases, and inevitability, right? False positive increasing. But let us take the mean error sum of squares. Okay, so that's what I want to show it to you. So here is the mean absolute errors or mean sum of squares or root mean sum of squares. When you compare that, what do you think is the bottommost 2 things? This last one, SVD. Do you agree with me? SVD, okay. And user based is this one. Do you agree with me? This and this, if you want to write it and show you 1 second, comment. So I'm saying this and this, this and this, this and this. Agreed, everybody? Of course, no, I'm not going to fight with the difference is big. No, definitely not. But systematically, you can trust that it's looks like this is what it is. Mostly, random item is supposed to be the wrong one, isn't it? So it is indeed wrong one. You can see this huge mean sum of squares, mean square error. Popular item is also somewhat interestingly good. Right? This one. Okay. So that's why I will use user based, and when I said that user based, even this this work in this publication, it shows that it's a good one. So don't waste your time. You don't have time. You have to recommend something. Just use user based SVD. That's my point. Agreed?
Okay. Okay. Yes.
So that's okay. Let's continue to go here. I don't know. It's not responding well. Gosh, this guy is getting hot. I don't know what it is. It is very hot in the machine. So, okay. So why don't you come back? Take you 5 minutes. It came back. Come back in 5 minutes. I will continue to explore the data and see what the recommender engine is doing for you, and we will conclude today about recommender engine. I will also I have another variation of this also. I will try to share that too. That's I'm trying to locate that one. Okay, so it is giving you some few things here. I wanted to tell you before you come back. So it is saying the number of you see the neighborhood average we took was 3. Remember that in the calculation, simple calculation I did yesterday. Here we are
Yes.
taking 30. And we are also considering the similarity is cosine similarity. We normalize the data because normalization is important. That tells you you take away the mean bias. Okay. So that is basically centering the data. That's what normalization is. And then you want to set some bounds, minimum bounds, that has to be satisfied, and that's what the alpha is. I will explain that. And with that, you got your results with whatever we did, and it created all these things in no time. That's my point, because it's a simple calculation. So recommendation engine is interestingly, except SVD, even SVD, with these are powerful computers nowadays, you can do a very good job of doing the computations very fast. So in no time, it calculates. This is the default values, and in no time it calculated all those things. So I just have to call them. If you call this one, the UBI, the user-based collaborative building, or SVD, I can get it because it's already part of the calculation done. Okay. Now let's come back in 5 minutes, and then you'll complete this exercise. There is quite a lot of explanation. I have to give a look at this one. It is here only right now.
Okay.
All right. Come back in 5 minutes.
Okay.
Thank you,
sir. Thank you.
I can't switch off. No, I still have to keep it. Put the computer on. Otherwise, if you switch off, then I have to install it. 5 minutes break is good. So don't I'm not closing this. When you come back, you will be here. No worries. But I will assign somebody, and then I will leave and then come back. Okay. You choose an organizer, leave. I'm going to choose Gaushali. Okay. Well, don't close Gaushali. Okay.
Sir.
Make